So glad everyone's paying attention. We should just had a food day.
Or are we taking it back to home?
What's that?
So are we taking it?
Phase changes. You guys have probably seen this before. I'm just going to talk about it briefly. I won't dwell too long on it. But do realize that if I go from solid to liquid, it typically melts. Just think of ice, if you will. Or liquid to solid, I'm freezing. We know about evaporation. We know about condensation. Sometimes you can sublimate. So that's going directly from solid to gas. No liquid interface.
Are we ever going to go into how pressure affects the phases of matter?
Next semester.
Okay.
So anybody know a common substance that we see all the time that sublimates? It goes directly from solid to gas.
Dry ice.
Dry ice. You've seen it where you, I think where you put it out at room temperature and it just smokes essentially, right? Or if you're having fun at a party, you put it in the punch bowl and it still goes from solid to gas and it creates bubbles and eerie smoke for Halloween. Anyone?
Oh yeah.
Thank you.
It's very.
So we're going to talk about some phase changes of matter and how that relates to heat of that we've talked about already, and heat of fusion and heat of vaporization. So this is the, you might want to sketch this in your notes, because then I'll just use this to talk about. I do want to point out a couple important things. I know it says heat here. What would the label be if I wrote it there?
Joules.
It would be joules, but what letter? Those are the units. What letter would I put here? Not delta H, not X. It is the x-axis. Clearly I know what this is. That's T, right? Temperature.
Would that be Q?
Say it again.
Would that be Q?
This is Q. Okay? All right? It's kind of important that we recognize this because we just talked about Q equals MC delta T, didn't we? And I want you guys to go back to pre-kindergarten when you talked about dependent and independent variables. You remember?
Yeah, pre-kindergarten.
In this equation, what is my dependent variable in this equation here? Q, right? And my independent variable is T, all right? However, when I look at this picture, this is very important you recognize this difference. When I look at this picture, what's my independent variable? Q is independent and T is dependent. Remember, X is usually independent and Y is usually dependent. So
Your MC would be.
it's like a slope. It's like some form of a slope here. So this is super important. Anywhere you see a slope, we're dealing with the equation Q equals MC delta T. Anywhere you see a flat line, what is that saying about the temperature? It's constant, it's not changing. But what's happening to Q? Q is going up, but the temperature is not changing. Do you see that in the picture? So I'm just going to sketch this. Are those degrees Celsius? They should be. And we'll talk about these various regions here. Okay. So it's super important you understand this. They have drawn the axes backwards relative to the formulas that we're using. Okay, so realize that as you're looking at it. Here's how I like to think about it. Tell me about the state of water, and this is water, by the way, but you can imagine this is true for a lot of solids to liquids to gases, okay? What's the state of water at negative 30 degrees Celsius? It's a solid, right? And this picture is telling me, right here, I have 0 heat put into the system. As I increase Q, remember this is really Q, as I increase the energy I'm putting into the system, what is happening to the temperature of the ice? It's rising, okay? That's this equation. There is heat going into the system, it's changing the temperature of the solid. Does that make sense to you? Okay? Then, oddly, we have this flat spot. Okay? Well, I haven't stopped adding energy to the system, Q to the system. Well, on this flat spot, I'm still adding Q, but what's happening to the temperature? Nothing. The temperature's staying constant. What's going on? Any ideas?
The ice is melting because it reached 0 degrees.
Correct. Here, I'm adding energy to the ice, the solid. The temperature's increasing up to this point, and then if I continue putting energy into the system, all that happens is all that energy goes to tearing apart the solid and turning it into a liquid. That's what's going on in this flat spot. I still add energy, but I'm not changing the temperature because the energy is going into tearing up the bonds of the solid and creating liquid. So in here I have a combination of liquid and solid, and then once I get to here, I have all what? Water. All water. And then if I continue to add energy to the system, I'm now on an equation that looks like this, except what's different?
C changes.
This is 4186, heat capacity of water in this region. And over here, if you look on your chart, there's a heat capacity of ice. So, same formula, except the heat capacity here is different from the heat capacity here. Are we following? Okay. Then what happens? Water's heating up, heating up, heating up, and I have this huge flat spot. What's going on?
All the energy is getting into.
All the energy that I pump in from here all the way to here is doing what? It's tearing apart the liquid, creating a vapor or a gas. Okay? And in this state, I have a combination of liquid and gas. And then when I get far enough, I put enough energy into the system, then I have all vapor. If I continue to pump energy into the system, I'm now on this equation. I keep adding energy, but what's the specific heat now? Is it in our chart for steam? It might not be. No? That's okay. So the idea here, I hope you understand what's going on in this picture. We are on the slope, Q equals MC delta T. Anytime you see an upward slope here, as I add energy, the temperature rises. If it's flat, I'm adding energy, but I'm tearing apart stuff. Does that make sense? Now let's chat about this and this. Right here, this is Q equals mass times L, and this is going from solid to liquid. When you go from a solid to a liquid, we think of it as, or let's think of it the other way. If I go from liquid to a solid, I'm like fusing things together, right? Creating a solid. This is called the latent heat of fusion. And you can look it up on a chart. There should be a chart in your book. And that will vary depending on the material that we're talking about. This M here, of course, is mass. When I go from liquid to vapor, that's the latent heat of vaporization. There's a V there. So depending on where you are on this chart will determine which L you need to use. Should be a chart. Here we go. So, water, the one we were just looking at, this would be in that very long region where we're putting a lot of energy into the system. And we're going from liquid to gas or vapor. That's the value you would use for ml. Got it? And then for the short flat location in the chart, we would use this value. So you can see that liquid takes a lot more energy, can take in a lot more energy than solid, or than the solid going to liquid. And of course it varies depending on what you're doing. Let me go for it.
Can you go back?
Maybe. Hang on a second. To there? To the chart?
Yeah.
Ah. There?
So that corner, that means like no liquid left.
What, say again?
That corner?
Here?
Yeah.
That is all steam right here. All
No
vapor.
liquid.
This is a liquid vapor combination as it's being torn apart, the liquid. Right at this point, we jump on the curve, and now as I add heat, I can raise the temperature of the steam above 100. It becomes super heated, so to speak. Now, let me just glance ahead here real quick, and we'll come back to the picture. I want to chat about a couple other things. All right, let me back up. Okay, couple things to think about. What happens if I go from here to there? Or from here that way? I am losing energy in the system. Okay? So energy is leaving the liquid or vapor, and it's going to the environment. Realize the way I approach this, I said as I add more energy to the system, whatever it is, I jump on these different curves and I start heading this direction. This is putting energy into the system. So putting a pot of water on the stove and turning on the stove, I'm adding energy to the water, and if I go long enough it boils, right? I'm adding energy. So interestingly, if I go this direction, I actually give off energy. It's exothermic versus taking in energy. Does that make sense? So I remember once when I was in high school, my high school physics teacher said, oh, if you're cold and you're hiking, you put out a bowl of water in your tent if it's super cold out, and as it freezes, it'll warm up the tent. It's actually true. Okay? Because what's happening, right? Temperatures are dropping, okay? And we're giving up Q instead of taking in Q. Okay? The danger of that is you spill the water and then you get wet and cold. But, you know, it would actually in theory work. Okay. Are there any questions about this? Because this will kind of come up again next semester in the sense of